Hi everyone. So in today's lecture what we're going to do is continue our counting principles, and the next section has to do with a principle called the pigeonhole principle. So what I'm going to be talking about in this particular section, I'm going to be basing on a section from Rosen's book, which is called Discrete Mathematics and its Applications. But you don't actually need that book to follow the lecture that I'm giving here. I'm just, if you want to find this book, you can see that the content here is presented. So what does the pigeonhole principle say? So if k is a positive integer and k plus 1 or more pigeons are placed into k pigeonholes, then there is at least one pigeonhole containing at least two pigeons. Okay, so let me kind of give you a visualization of this before we actually prove it. So suppose that I had three, well, you can think of them as bins, but you can also just call them as pigeonholes. Okay, so let's say that I had three bins. Okay, and then suppose I have four pigeons. Okay, or more. So if I had four pigeons and I started to place them into these bins, well, how could I do that? I could do that in a bunch of different ways, right? But since I have four of them, I'm going to be guaranteed that there has to be one of these bins that has at least two pigeons in it, because at the moment you can think of these dots as placing the pigeons, right? So let's say that I place first pigeon in the first bin or pigeonhole, second pigeon in the second pigeonhole, and then third pigeon in the third pigeonhole. And now I still have a fourth pigeon, right? So this fourth pigeon is going to fly in, and now it has to go to one of these pigeonholes, but what that means is it's going to have to go into one that's already occupied. So let's say that it flies into this one. And so now I'm guaranteed that this situation will have to happen. There's going to be at least one pigeonhole containing at least two pigeons. Okay, and now you can use this idea for many, many other contexts, and I'll give you a bunch of examples in just a second. But you can kind of think about that intuitively, right? Like if I have three bins, and you could just think of them as balls instead, right? So let's say that I have three bins, and I have to put four balls into these bins. No matter how I do that, there's going to be one bin with at least two balls in it, right? You could have a bin with all four, and the other two are empty, right? But then that first bin would have four of them, which is at least two. Okay, so you're kind of looking for, well, that's just what the principle says. Okay, so let's prove it. Okay, so the proof that we're going to do here is we're going to do a proof by contradiction. So proof by contradiction. Okay, so first what we're going to do is suppose this condition, right? So suppose k is a positive integer, okay, and k plus 1 or more pigeons are placed into k pigeonholes. Okay, so if it was a direct proof, we would just have to show there is at least one pigeonhole containing at least two pigeons. Okay, but by proof by contradiction, we're going to suppose that none of the k pigeonholes contains more than one pigeon or object, right? One pigeon. Okay. Well, what does that mean? Well, if you suppose that none of the k pigeonholes contain more than one pigeon, then what's the total number? Okay, so then the total number of pigeons would be at most K, right? Because you're saying suppose that none of the K pigeonholes contain more than 1. So you can kind of think of this as adding either 1 or 0 for each pigeonhole. So then the total number of pigeons would be at most K. However, the original assumption was that there was K plus 1 or more pigeons that are placed into these K pigeonholes. So that's the contradiction right there. So this is a contradiction. This is a contradiction. Okay, because there are at least K plus 1 pigeons, right? It was assumed that there's K plus 1 or more. Okay, so therefore, this assumption that suppose none of the K pigeonholes contains more than 1 pigeon is false, which would mean that we have our conclusion, right? That there is at least 1 pigeonhole containing at least 2 pigeons. Okay. Yeah, I know when you're kind of saying these phrases, it sounds a little bit unintuitive, but if you just kind of think of it as, using this first example, it makes a little bit more sense. Okay, so let's do a bunch of examples now. Okay, so let's do some simple ones. Okay, so in a group of 367 people, so let's say that you just have a group of 367 people, there must be 2 people with the same birthday. Okay, well, why is that? Well, this is because there are only 366 possible birthdays, right? We're just talking about the day. We're not talking about, so the month and the day, we're not talking about the year as well, right? So this is because there's only 366 possible birthdays. This is including leap year, like this year, right? And so therefore, by the pigeonhole principle, since you have 367 people, even if you were to distinctly list all those birthdays out, there's going to have to be, once you get up to this 367th person, you're guaranteed that last person is going to have to repeat one of the previous ones, right? So you could pretty much just say that. So by the pigeonhole principle, there must be a repeat birthday with 367 people. Okay. Now, it's probabilistically, it's actually much more likely to happen with fewer people. Actually, this is kind of an interesting probability problem. You could look at this, look this up. It's the birthday problem. So, if you want to look that up, it's kind of an interesting problem. Okay, so another example. So in any group of 27 English words, okay, so just give me 27 English words, there must be at least 2 that begin with the same letter. And this, again, is also by the pigeonhole principle, because there's only 26 letters in the English, alphabet. So once you get to 27 words, you're guaranteed there has to be at least 2 that begin with the same letter. This is, again, by the pigeonhole principle, right? Because there are 26 letters in the English alphabet. Okay, so that's another example of a pigeonhole principle. Not too crazy. Other alphabets you might need more words, like for example Russian uses Cyrillic. I think there's 33 letters in Cyrillic, so you'd need 34 words, right? But I don't think all Russian, there are some words that don't start with certain letters, I think. But anyway, let's just think about these examples. Okay, in a group of 677 people, there must be 2 people with the same first and last initial. Okay, and we're assuming we're using the English alphabet again. Well, why would that be? Well, let's think about how many combinations can you have for first and last initial. So how many choices for first initial? Choices for first initial. Well, we're using the English alphabet again, right? So first initial, you could have 26 letters, right? And then what about the second? Second initial also has 26 choices. So you have 26 squared choices. And I believe that this is 676. So if we have 677, which is one more than this, there must be a repeat. So this is total possibilities for first and last initials. So with 677 people, there must be a repeat. Right? Okay, again, that's by the pigeonhole principle. And you could say that. You could say by the pigeonhole principle. But that is effectively how it works, right? So you're thinking of these combinations as the pigeons, right? And the number of pigeonholes that you're thinking of the first and last initial that you have for each person is, the people are the pigeons, right? And they have a first and last initial. And then the pigeonholes are these combinations. And we calculated how many total combinations you have. So there has to be a repeat in there somewhere, right? So I'm just trying to draw the analogy between the pigeonhole principle. But you can kind of see how that's just an abstraction of what you're kind of doing in each of these problems. Okay, 2 members of this class were born during the same month. Well, to be guaranteed, our class has more than how many people do we need to be guaranteed that? We need at least 13, right? Because there's 12 months. So as soon as you have a 13th person, then you'd be guaranteed, right? Has more than 12 people. I think there's actually 42 to be exact, and that's including both sections. So there must be a repeat, okay? Since only 12 possible months, right? For you guys to be born in. All right. In fact, it's kind of interesting to think about how large this number is and how many repeats you could actually be guaranteed, right? So once you actually get beyond 24, does that actually guarantee there's got to be 3 people with the same birth month, right? So that might be kind of an interesting generalization. Once you get to like the 25th person, right? You could kind of have 2 distinct people for each month. That would be 24. And then once you get to that 25th, I think you'd be guaranteed that you actually have a third person that must share a birth month with 2 others, right? So you have a triple and so on. So actually what would be next would be 36, right? So 42 is still greater than 36. So let's think about that. Okay, here's an interesting problem. All right, I kind of write out the proof, but I'll add into it in just a second. So show that for every integer n, there must be a multiple of n that has only 1s and 0s in its decimal expansion. Okay, so here's kind of the clever argument here. So what you're going to do is consider these numbers. So here's a list of numbers. So you have 1, 11, 111, then you have 1,111, and so on and so forth until you get to this number right here. So this is one number, and this last integer is in this list is the integer with exactly n plus 1 ones in its expansion. So n plus 1 ones here. Okay, so that's the number with n plus 1 ones. Okay, now here's the clever part. So if you divide each of these numbers in this list by n, you can compare the remainders. Okay, now what are the possible remainders when you divide by n? Okay, so let's write that down here. So if I had a is one of these numbers, right? And we know from the division algorithm that you can always write a as n times some quotient plus a remainder, right? And what are the possibilities for this remainder here? So this remainder, you definitely know, is either 0 or all the way up to n minus 1. And these are integers. So there's a total of n possible remainders, right? So you have 0, 1, 2, 3, all the way up to n minus 1. So there's n possible remainders. So you can do that for all of these, okay? But since there's n plus 1 of them, what does that mean? There actually will have to be another one that looks like this. So let's call this Q1 and this Q2, but they will actually have to have the same remainder. Okay, and that's because of the pigeonhole principle. So by the pigeonhole principle, there must be two that have the same remainder. Because why is that? Well, there are n plus 1 numbers here. Okay, so this is because so there are n plus 1 numbers in this list. Okay, so by the pigeonhole principle, there must be two that have the same remainder. So a little explanation of that. There are n plus 1 numbers in the list, but only n possible remainders. Okay, so does that kind of make sense that by the pigeonhole principle, there are n plus 1 numbers in the list, and if I divide all of them by n, there are only n possible remainders. So in that list somewhere, there must be a repeat. So it would look something like this. So you'd have a is one of these numbers up here, b is one of these numbers up here, and they both have a quotient, but they actually have the same remainder. Okay, so same remainder. Okay, isn't that kind of cool? That's guaranteed by the pigeonhole principle, that this is guaranteed. Okay, now what can we do with this? Well, if you take the positive difference of the two, all right, what do I mean by that? So if you consider a minus b, and let's say that this is the bigger one. Okay, so in this list, a and b, one of them is going to be the bigger number. And so when I take this difference, if I take the bigger number and subtract the smaller number, I'll have a positive number. Okay, but what is this? I can substitute my two equations. So I have nq1 plus r, okay, and then I subtract nq2 plus r, right? And if I do the subtraction, look at what you get. You get nq1 plus r minus nq2, and then this negative gets distributed minus r. And so you see these remainders actually cancel because they were the same, right? So when I take this difference, I actually get n times q1 minus q2. So do you see that n is actually a divisor of a minus b? So take the positive difference of two such numbers, and that number will only have ones and zeros, okay? And its decimal expansion, or in its decimal expansion, and it will be divisible by n. So this equation shows you that it's divisible by n. So n divides a minus b. And then why would it only have ones and zeros in its decimal expansion? Well, if you take any of these two numbers and you subtract the positive one by the subtract the bigger one by the smaller one, you're going to get a number that only has ones and zeros in it. For example, just look at if I took like 111. Let's say A was 111 and B was 11. If I subtract that, what would I get? I'd get 100, right? And that has ones and zeros in its expansion. Okay, but that's going to be true with anything in that list. Okay, so that's sort of the clever way that you can first use I just wanted you to see this example because you can use pigeonhole principle to kind of guarantee the existence of something, right? That's the first step, is this, that A and B exists, and then you are able to extract a little bit more information from it. So that's, in a lot of situations, how the pigeonhole principle is used. It's used to show the existence of something, and then you can extract a little bit more information from it. So it's actually, it can be quite powerful, actually, especially in a more general situation. Okay. So let's look at kind of an interesting corollary to this that involves functions in general. So a function from a set A where the cardinality of A is at least k plus 1 to a set B where the cardinality of B is equal to k cannot be 1 to 1. So let me kind of draw a picture for you, right? So let's say here's a specific example. This is not a proof. Okay, so the proof we're going to do down here, but here's an example. Let's say that this is A and this is B. Okay, and let's say, so let's say A has 3 objects in it, right? A1, A2, A3. So the size of A is 3, right? So there's exactly 3 objects here, and this is like your k plus 1, right? So in other words, I just want to make sure that the cardinality of A is strictly bigger than the cardinality of B. Okay. Okay, so let's say that B has 2 things in it. Okay. It could also have 1, and it would follow this situation, right? Because you just want to make sure the cardinality of the domain is strictly bigger than the cardinality of the codomain. All right, now if I try to create a function, look at what will happen here. So A1 has to get sent somewhere, okay? Okay, so it has to get sent to, let's say, B2. Okay, now A2 has to get sent somewhere. Okay, and it can go to either B1 or B2. Okay, but if it goes to B2, it'll definitely not be 1 to 1 anymore, right? Because then I'll have distinct things going to the same thing. So kind of, if I'm trying to maintain being 1 to 1, the only other choice is to go to B1. Now you get to this last one. So A3, you can kind of see how this is like the pigeonhole principle. You can kind of think of these as your pigeons, and here are the pigeonholes, and the pigeon has to fly to one of these pigeonholes, right? As a function, A3 has to have an output, right? So A3 has to fly to one of these possible outputs. It's either got to fly to the first one or the second one. In midair, it has to make this decision, right? So what is it going to do? Well, if it goes to the first one, then it fails to be 1 to 1. And if it goes to the second one, it fails to be 1 to 1, right? Because if it goes to that first one, you see that it's distinct from A2, but they have the same output. And if it flies to B2, it's distinct from A1, but then it has this repeat of B2. So you see in either situation, it's not going to be 1 to 1 anymore. Okay, so that's exactly how the proof actually works. So the proof just effectively says, treat these elements of the codomain as these bins. Okay. Okay. You kind of have these bins, okay? So let's just kind of write this out. So suppose that for each y in the codomain B, we have a bin that contains all the elements x from the domain A such that f of x is equal to this y. Okay, so we have these, you can call them x1 and x2, and let's say that they go to these bins. Okay, so each of these bins contains all of these elements. Okay, so because the domain contains k plus 1 or more, okay, k plus 1 or more elements, and the codomain which is B, right, contains only k elements, then by the pigeonhole principle, that tells us that one of these boxes must contain 2 or more of these x's from the domain, right? Then the pigeonhole principle tells us that one of these boxes, or bins, right? Bins contains 2 or more, right? 2 or more of these x's from the domain. Okay? And that means that f can't be 1-to-1 because then you have two distinct elements that are in the same bin, effectively. So they have the same output. So that means that f cannot be 1-to-1, right? It would be as if you have an x1 and an x2, and you could have more, possibly more, where f of x1 is equal to y and f of x2 is also equal to y, but these are distinct elements from the domain. So f is not 1-to-1. Okay? And then similarly, you can actually play this game to show that a function from a set with k elements in it to a set with greater than or equal to k plus 1 elements cannot be onto. So let me just draw kind of a picture for that other one, and you can try to think about the general proof of that. But if you kind of flip them, okay, so if I have 2 objects and I'm going to a set with 3 objects, right, I could map the first one somewhere and the second one somewhere, and then I'm going to have some leftover elements, right? So leftover element not in the range or the image. Okay, so it's kind of like you have these pigeons and you have too many pigeonholes, so there's going to have to be one that's left over, right? Okay, so is there some generalization of this? I kind of hinted at that before with the example of how many students in the class and the birth months. Okay, so this would be the generalized pigeonhole principle. So if n pigeons are placed into k pigeonholes, then there must be at least the ceiling of n divided by k pigeons in a single pigeonhole. And then similarly, there must be a pigeonhole with at most the floor of n divided by k, if you take the floor of that, pigeons. Okay, so let's instead of trying to prove this in general, because it can get a little bit complicated with an inequality that has to be involved here, I just want to give you some intuition behind this. So let's say that you had 6 objects, right? Or you know what? Let's start off with maybe a little bit more intuition. So let's say you have 7 objects, okay, and you have to put them into 3 bins, okay, 3 bins. Okay, then we must have a bin with more than 2 objects. Okay, in other words, we're saying at least 3 objects. Now, where's that coming from? Well, that 3 is actually the ceiling of, if you take 7 divided by 3. If you take 7 divided by 3, what is it? It's 2 and some change, right? Of course, you can tell me the exact answer, but the point is that if you round up, you'll have 3, right? Okay, so let's think about the intuition here. So if I have 7 objects and I start to place these in these bins, okay, if I'm trying to sort of think about this, I start adding these in. okay, I reach sort of a critical situation where I have 2 in each bin, all right? But as soon as I get to the 7th object and I have to put one of them in one of the bins, no matter where I put it, I will be forced to have at least 3 objects in the bin. You see that? So let's say that I put it in this 3rd one, then this bin has at least 3 objects. Now you could have done that in a worse way, and then you would have gotten to the conclusion even faster, right? I could have actually just started with the first bin, and I could have just put all 7 of them in that first bin. But I still get the conclusion that there are at least 3 objects in one of those bins, right? So I must have a bin with at least 3 objects. Okay. If I had 6 objects, right, then I'd only be able to guarantee that there's a bin with at least 2 objects, right? You wouldn't be guaranteed one with this 3rd one, and that's where you kind of have this this rounding up won't really affect it, right? Because 6 divided by 3 is 2, and then the ceiling of 2 is just 2. Okay, but even if you have a little bit more when you do this division and you have to round up, you can't just have, a fraction of an actual object. So because of that ceiling, I actually know that I have, as soon as I have a little bit more, then I have an entire object that I'm talking about. So going back to our actual month example that we had before, if we have 42 students, right, we can kind of abstract that problem and use the generalized pigeonhole principle, right? So we have 42 students, and we have 12 possible months, right? 12 months, and each one of you has a month that you were born in, okay? And one question might be, what could we guarantee? So by the generalized pigeonhole principle, right, there must be a month. We don't know which bin it actually is, but there would be one month, just like there's a bin. Okay, there must be a month with at least 42 divided by 12, and then we can take the ceiling of this. So this is 3.5, right? Right, because 36 is 3, and then you have 6 more than that, so that would be a half, right? So you actually have 3.5, and the ceiling of that would be 4. So there actually must be a month where 4 of you have a common birth month, where you all were born in that month, right? And we're guaranteed that from the pigeonhole principle. There must be a month with at least that many. Now, it could be possible that all of us were born, say, in the same month. That is a possibility, and that still satisfies the condition, right? That there must be a month with at least that many students. So keep in mind that the pigeonhole principle just kind of gives you this guarantee, but it doesn't give you more information than you might think. We don't know exactly which one it is, and it could actually be much more than that, right? It's just kind of giving you a bare minimum, right? So there could be you could kind of think about the maximum. The maximum would be 42, right? You could have theoretically a month with all 42 of you that shared that birth month, right? That would be the upper bound, which would be the number, right? But then the lower bound is kind of an interesting one that's given by this generalized principle. Okay, so let's start to look at some related problems like this, and you can kind of see how they can turn into some non-trivial ones pretty quickly. So suppose that you have 3 red marbles, 5 green marbles, and 7 yellow marbles in some bag. Okay, so they're all in that bag. And how many marbles would have to be chosen so that 2 of them were the same color? Well, okay, so if you can't see those marbles, right, and you start to reach in, you could pull out the first marble, and it could be red, green, or yellow, right? Then the second one you could pull out, and it might be the same color. So it could actually happen at minimum by choosing 2, okay? But we want to guarantee, if I were to choose a collection of them, right? How many marbles must be chosen to guarantee that you have that many? Like, let's say that you chose them and then you were to look at them, Okay, how many would you have to choose to be guaranteed this? Well, you would have to choose 4, right? Because in a worst case scenario, the first 3 were all different. Okay, but as soon as you choose that 4th one, because I'm going to have to repeat one of these colors, then you'll be guaranteed that it'll be a repeat, right? So it'll be 4, right? So as soon as you choose, again, so the first 3 could have been distinct, right? But as soon as you choose that 4th one, it's going to match one of the previous 3 that you've chosen, and therefore you would definitely have a pair. Okay. What about 3 of the same color? Well, kind of playing that same game, the first 3 you choose could be distinct, and then you could start to repeat things, right? So the second one, the 4th one you choose, let's just say that it goes like red, green, yellow, and then it goes red, green, yellow again. Then you see that you have 2 of the red, 2 of the green, and 2 of the yellow, and you still don't have 3 of the same color. But as soon as you choose that 7th one, okay, then we're kind of playing the same exact game that we kind of had in this first example up here, right? As soon as you choose that 7th one, then you know that you're going to have a bin that has at least 3 objects in it. So that would be the situation that we have here, right? So you would have to choose at least 7, right? So if I choose 7, I'll be guaranteed that I have at least 3 here. If you kind of want to turn these into algebra problems, you can do that, right? This first one, you could kind of think of it as, all right, well, we still have these are your bins, right? So you have sort of your 3 bins, and you're trying to solve this. You're trying to solve what is, how many objects do I have to have amongst those 3 bins to be guaranteed that this is 2, right? So if n was 1, then it'd be a third, and I round up, that would be 1. If I had 2 thirds round up would be 1, and then 3 thirds, right, or 1 round up would be 1. But as soon as you get to 4 thirds, right, so n would actually be 4, because as soon as you get to n equals 4, 4 thirds is 1 and a third, right? You have 1 and some change, but when you round up, that'll be 2. So as soon as you have that 4th object, right, you're going to have a repeat here. Similarly, down here, it's kind of like you still have those 3 bins again. Okay, and if I do n divided by 3, and I take the ceiling of this, right, round up, then I want this to be equal to 3. Okay, and that you're finding the smallest n, right? Smallest n to guarantee this. Okay, because this has multiple solutions, but you're trying to find the smallest n that guarantees that. Same thing down here. So the smallest n would be 7 here, right? Because if you get to 6 over 3 is 2. The ceiling of that is still 2. But as soon as you get to 7, you have 2 and some change, right? 2 and a third, and rounded up, that would be 3. Okay, so that's how we're getting that number. But intuitively, you can kind of see the picture up above, how we were thinking about that. But here you can kind of see how you can turn it into an algebra problem using the generalized principle. Okay, what about 2 green marbles? Okay, now the bag itself has 3 red marbles, 5 green marbles, and 7 yellow marbles. Okay, but what you're trying to do is guarantee that I have 2 green marbles. So for this one, you kind of want to think about the worst case scenario, right? In the worst case scenario, you would choose all the reds and you would choose all the yellows before you start choosing the greens, right? Which is a possibility, right? I'm not saying it's likely, but in the worst case scenario, that actually is possible, right? You could choose the 3 reds and then the 7 yellows, which would be 10 marbles. You could theoretically have chosen 10 marbles out and not even chosen a green yet. And then now once you get to the 11th one, you have to pick a green because there's no other left. And then finally, the 12th one would also have to be green. So to be guaranteed this, it would actually be 12, right? Because that's sort of the worst case scenario again, where you chose 3 red, and then 7 yellow, or a combination of those. It doesn't have to be exactly in that order, but you chose all the red and yellows before you chose any greens. Okay, and there's lots of different combinations that would produce that situation. But 12 would absolutely guarantee it. although it probably would happen, a separate question would be, you could explore the probabilities of these, right? It's probably more likely that it would actually happen before this in general. Okay, so I thought you might like some of these problems. Okay, and then lastly, I wanted to show you an application to an entire area of combinatorics called Ramsey theory. So here's sort of a problem. It's one of the first problems in Ramsey theory. So the original problem is actually stated like this down here. I'll give you the alternative problem first. So let's say that you have this party with 6 people, and consider any 2 of them at this party. Now, they might be meeting for the first time, in which case you'll call them mutual strangers, right? They didn't know each other before this party. Or they might have met before, and they know each other before, in which case you'll call them mutual acquaintances, okay? So the theorem says this. So at any party of 6 people, either at least 3 of them at the party are pairwise mutual strangers, or at least 3 of them are pairwise mutual acquaintances with each other. Okay, and this was originally kind of there's an entire article written on this, which is kind of interesting on Wikipedia if you want to look at this a little bit more. This is called the theorem on friends and strangers. So let's propose the problem in a different way. Okay, so let's say. Okay, let's assume that in a group of 6 people, each pair of individuals consists of 2 friends or 2 enemies. So in this group, they're all friends or enemies with each other. Okay, similar to the previous way that we posed this, but instead we have friends and enemies. Okay, now show that there are either 3 mutual friends or there are 3 mutual enemies in the group. Okay, so that's kind of an interesting deduction that you could propose in this situation. Okay, so let me try to give you a visualization for the initial setup of this, and you can kind of see how the pigeonhole principle can be used, a generalized version. Okay, so you have 6 people. Okay, so let's okay, so we have person 1, person 2, person 3, person 4, person 5, person 6. Okay, and now let's isolate person 1, and we'll call that person A. Okay, now the remaining 5 people are going to go into one of 2 bins. Okay, so these bins are either the friends of A or they are the enemies of A. Okay, these are the only 2 possibilities, and all of these 5 people must go into those. All right, well, by the generalized pigeonhole principle, what can we say? So one of these bins must have 3 or more elements, right? And that's just by the generalized pigeonhole principle. Since each bin or set, you could think of them as a set of people, has at least there's 5 people, right? And there's 2 bins. So 5 over 2, and you take the ceiling of this, right? So the ceiling of 2.5, so you round this up and you have 3, okay? So there are either 3 enemies or, so there are either 3 friends or 3 enemies of A here. Okay, so let's explore those 2 cases. So case 1, there are at least 3 friends of A. Okay, so let's say that this bin had the 3 people in them, whatever they may be. Okay, so let's relabel those people, the P2 through P6, but whatever ones end up in there, we can call them B, C, or D. Okay, so we can call them B, C, and D. Okay, now if any two of these three are friends, then these two friends together, these two friends together with A would form a set of three mutual friends, right? Because we already knew that B, C, and D were friends with A. So if there are any two among these three that are actually friends, then these two friends together with A would form a set of three mutual friends. Three mutual friends. And that would solve our problem, right? Because we're looking for three mutual friends or three mutual enemies. Okay, but what if B, C, and D are all enemies? Well, that could happen, right? So otherwise, all three B, C, and D form a set of three mutual enemies. Sorry, little delay here. Hang on. Form a set of three mutual enemies, which would also solve the problem, right? Because we are looking for a guarantee that you have a set of three mutual friends or three mutual enemies, and that would happen in this situation. Okay, and then case 2 is pretty much the same idea here. So case 2, there are at least three enemies of A. So that's assuming that you were in the other case, that this bin was the one that had at least three enemies of A. Okay, well, in that case, you can call the three, at least three of them. You can pick any three. It doesn't matter which one. Just like up here, you had at least three. You can call any three of them B, C, and D. All right, so we can call any three of them. Call any three of them B, C, and D. Okay, and then if any two of these are enemies, then what happens? So if, let's say, B and C are enemies, well, A and B were enemies and A and C were enemies. So with A, we get three mutual enemies. So with A, we get three mutual enemies. Okay? So if any two of these were enemies, then with A, you'd get three mutual enemies. And then otherwise, B, C, and D are three mutual friends. Okay, you have three mutual enemies or three mutual friends, and in any of these possibilities, you end up with what we wanted. Okay. Now the only other thing that's left was that A was arbitrarily chosen. Okay, but you could do the same process with any six of them. Okay, so you could have picked the second person to be your A, or so on, and the argument would be exactly the same. So it's definitely a non-trivial deduction, but keep in mind that in the end, you're showing that there are three mutual friends or three mutual enemies. Okay. So that's definitely a non-trivial deduction. This is actually, there's an entire area of mathematics devoted to problems like this. And the whole area is called Ramsey theory. And it's generally considered sort of a portion of combinatorics and discrete mathematics. But the general types of problems that you would see in this field are very general questions where you have something like this. You would say, how many elements of some particular structure must you have in order to guarantee that a particular property is to hold? All right, so this original problem was kind of translated in several different ways. So I just was showing you one where you could think of it as mutual friends and enemies. Another way is with acquaintances and strangers. You could actually think of it structurally as well as a graph theory problem. If you're interested, maybe I could draw you a picture for that. So if you're interested in this alternative version, there's an entire Wikipedia article where I kind of take this from. If you just search theorem of friends and strangers, you can actually see all the possible graphs that you can have. So I wanted to just kind of give you an idea of how how it works as a graph theory problem. As a graph theory problem, you kind of have those 6 people as what you'd say are vertices, okay? And then you have edges between them, okay? And the edges are you kind of are drawing like a social network here. And so this person effectively, you kind of have, think about our first example, the friends and the enemies. Okay, so you have they know each other, you draw an edge between them. Okay, I'm not drawing in whether or not they're friends or enemies just yet. Okay, so you have all these connections. So you kind of have an idea of whether or not 2 nodes know each other, and that's kind of an example of a social network. Okay, I think we have all of them, right? Okay, so this actually is called a graph in general. So you have vertices, and then you have edges, which are the connections between them. All right, this particular graph is actually called a complete graph because you're drawing in all the possible edges between them. So you have 6 people, and they all know each other. So you have this example of a social network. Now, the original problem is those 6 people are either friends or they're enemies. Okay, so if they're enemies, what you could do is, instead of using, let's say that blue represents they're friends with each other. Okay, and and then you could also draw it with a red, and a red line between them would mean that they're enemies. Okay, so in general, these 6 people, you have friends and you have enemies. Okay, so let's say that this actually was the situation that you had. You had these 2 are enemies, these 2 are enemies, and these 2 are enemies. Now, if you stare at this graph, the original problem was among these 6 people, there are either 3 mutual friends or there are 3 mutual enemies. So structurally, what that would look like is we're looking for either a red triangle, which would be 3 mutual enemies, or we would be looking for a blue triangle. Now, this particular situation has lots of blue triangles. Do you see that? Let's call this. Let me give them labels here. So let's say that that's A, B, C, D, E, F. Do you see that A, D, and E are mutual friends? And do you see that the triangle between them is all blue? So they're 3 mutual friends. Okay. Do you also notice that there is no triangle where there's 3 mutual enemies? Okay. There's no red triangle. There are actually lots of blue triangles. Do you see that D, B, and E are 3 mutual friends? You have A, C, and D are mutual friends. You have B, E, and F are mutual friends. Okay. But that problem says no matter what setup you actually would have, that will happen. Okay, so you could actually have sort of interesting situations where you have lots more enemies, and then it could become a little bit more non-trivial in general. So there's a whole area of math called graph theory where you try to abstract certain setups using graphs, and then you turn the problems into graph theory problems. That's actually the area of research that I work in. But I also usually work with much larger graphs, and we use algebra and linear algebra like matrix analysis to study the graphs. Okay. I just wanted to show you how you can kind of turn this into a structural problem.